So let's talk about trigonometry. I'm going to talk about some basic sort of concept things first that I think you know, but maybe it's not a bad idea to review them, and maybe some of them I'll present here in a slightly different way than what you've seen before. So we'll start with our old friend, the unit circle. Since this is a unit circle, it's called the unit circle because it has a radius of 1, right? And if you wanted to write down the equation that describes this curve, it would be this. So if we pick a point on this circle, let's just call it some generic point x comma y, then we know that if we make a segment that goes from the origin to that point, and we have an angle here, we could call theta, and we know we define the sine of theta is equal to the y-coordinate here, and the cosine of theta is equal to the x-coordinate. This is one way of defining what sine and cosine are. It's not the only way. You have your geometry way, your SOHCAHTOA kind of way, right? Right triangle definitions of sine and cosine. And this jives perfectly with that. Because if, for example, let me just write down here, you know this SOHCAHTOA, it's a useful little mnemonic device to remind you that the sine of an angle is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is equal to opposite over adjacent. This is for right triangles. Of course, you wouldn't be saying the word hypotenuse if it wasn't a right triangle. And that's still true here, right? If we wanted to draw in the sides of this little triangle here, then this part here, well, that's the x-coordinate, and this part here, that would be the y-coordinate. And sine is opposite over hypotenuse. Let's see. The sine is opposite, that's y, over the hypotenuse. And the hypotenuse here, because we're inside the unit circle, the hypotenuse is a radius of the circle, which is 1. So sine is y over 1, or just y, and cosine adjacent over hypotenuse is x over 1, or just x. And the tangent of an angle is equal to, probably you excuse me, remember that it's sine over cosine, but here that's y over x. Or sine over cosine, if you prefer, right? Same thing. And of course that's opposite over adjacent. Right? So the unit circle is nice because it takes the scaling of all different right triangles and it forces them all into this mold where the hypotenuse is always 1. Any triangle that you draw in this way, connecting the origin to a point on the circle, always has a hypotenuse of 1, if you consider the x and the y coordinates to be the legs. Alright, so there's that. Now, what about this angle? We in calculus class are 99% of the time going to measure angles in radians. And there's a really, really good reason for that that I can't really quite explain to you yet because you don't know any calculus yet. But the reason is a radian is kind of an objective measure for an angle that's not tied to any kind of arbitrary, well, let's just take a circle and we'll divide it up into 360 degrees. That seems so natural to us because that's been part of our mathematical training since the first time we ever thought about degrees and angles. But it's really an arbitrary choice. Why would you divide it up into 360 degrees? You know, it works pretty well. 360 is evenly divisible by lots of different numbers, so that's nice. But it is an arbitrary thing. And radians are, in a way, more objective. So let's talk about, make sure we understand what is a radian? Well, a radian is a way of measuring an angle, and if you're in the unit circle, it's the length of this piece of the circle. So what is the measure of this angle? Well, it's how long this arc is right here. And I know, for example, the whole circumference of the unit circle, circumference of any circle is 2 pi r, but since the radius here is 1, the circumference of the unit circle is 2 pi. So that means if you go all the way around, in other words, if you have an angle that goes all the way around, an angle that we could call 360 degrees, that corresponds to the entire circumference, or 2 pi worth of angle measured in radians. And then everything else divides up from there. So this would be pi, right, because that's this much of the circumference. And then this would be pi over 2, would correspond to an angle that we could call 90 degrees, and so on. So that's what radians are. And more generally, you could say that radian measure of some angle oops, that was supposed to go to the center of that. I kind of missed there. Let's scribble that out and try that again. So let's say we have some angle theta here, and the radius of my circle is r, and we could call this is the subtended arc. We could call that S, is the name for that we use usually. So the angle measure, theta, is just S over r. Of course, if your circle happens to be the unit circle and have a radius of 1, then that is just S, the length of the arc. But in general, the radian measure of theta is defined like this. And also, whatever we're measuring our circle in, if these happen to be centimeters or millimeters or inches or miles or light years or who knows what units we might be using, notice that this is a ratio of a length to a length. So a radian is actually dimensionless. It doesn't have any inches or things like that associated with it. It's a ratio of one length, this one, to another length. So whatever units you were using, they would cancel out. And that's nice too. It's part of the objective standard of radian measures for angles. Right, now what else do we want to talk about? Maybe, I don't know if you've ever thought about this. Why is tangent called tangent? Because there's another sense of tangent that you know from geometry, right? That if you had a circle, for example, and you have a point here, you could draw a tangent line. So there's that, right? What does that have to do with this thing that's like the tangent function in trigonometry? Are they related? Is there something about the meaning of tangent that applies to both situations? And the answer to that is yes, there is. So the tangent line here, we call the tangent line because at this point, the line and the circle have the same slope. And in calculus, we're going to be very, very interested in finding slopes of things that are not straight lines. Now, if you have something like a circle or any other curve, something that's not straight, I think, well, how can you define the slope of that? And we'll get into that in Chapter 3 at the very beginning of next year. But suffice it to say right now, you could imagine if there was a little car driving around this circular track, the slope of this curve is the direction the headlights are pointing in at any moment. So for a point right here, for example, the slope would be vertical. For a point right at the top of the circle, the slope would be horizontal. And as it goes on, you can imagine the headlights and taillights shining out, making this beam that is like the direction that the curve is going in right at any instant. So curves do have slopes, and we'll do quite a lot with that. And the tangent line just is the line that goes through that point and has that same slope, so they agree, right? And if you have just the right slope, you might be more familiar with the definition that the tangent line only goes through one point of the circle. It doesn't accidentally like hit another one or something like that. And those two definitions agree with each other. If you manage just to hit one point, then it's because you actually have found the line that has the exact same slope as your curve. So, tangent has everything to do with slope. And if we look back over here, the tangent of theta is equal to y over x. Y over x. Y over x, well, that's like rise over run. So the tangent function here is kind of like the slope function. In fact, it is the tangent of an angle here, theta, in the unit circle. It's the slope of this line, or this line segment. So both of them have to do with slope. And that's a good thing to know, I think. And if you're wondering, well, what about other things? You remember what you call a line that goes through 2 points of a circle like this? This is called a secant line. Now, what does that have to do with the secant function? Well, it has, you can kind of force it into a agreement with the unit circle, at least partially. If you think about the other point here, if you use the point here, 0, -1, down here, and you connect this to your point, the slope of that line is the secant of the angle. So for example, if you want to know what's the secant of 0, you draw this line, and that line has a slope of 1, and the secant of 0 degrees is 1. It's 1 over cosine 0, which is 1 over 1, and so on. And you can see that when you get up to pi over 2, you'd be drawing a vertical line, so the secant of pi over 2 is undefined, and so on. So those are some kind of cool connections to make, I think, help ground your understanding of the vocabulary around trigonometry. Now, what about actually finding values of trig functions? In other words, what if I ask you, without a calculator and without agonizing too much, what's the sine of 7 pi over 6? Like, what is your thought process there? Maybe you just, at some point in Algebra 2 at the end of the year, or in pre-calculus, maybe you just memorized all those, and maybe you just know right immediately. Or maybe you did, because you had a unit circle quiz or something like that. But if you don't have those memorized, and I will confess to you that I don't, I've been teaching calculus for a long time, and I don't have these things memorized, so I cannot immediately tell you what that is, but I can do it very, very fast by thinking about it like this. And maybe you kind of do the same thing here, but I just want to review this. So I don't actually draw this, I just imagine a unit circle. So this is all happening in my mind. And the one thing you do need to be able to do is locate that angle. Right? You need to know where that is. So there's different ways of thinking about that. I would think about this as being pi over 6 past pi, right? That's like pi and a sixth, because 7/6 is like 1 and a sixth, right? So that would be here, right? It's like 30 degrees past 180 if you want to ground it in degrees. So we're talking about this angle. That's my theta. Okay, and I know the sine is the y value. Well, every single one of these so-called nice angles, all of the pi over 6s and pi over 3s and pi over 2s, they're all either they're all either like right on the axes, which are the easy ones, right? You know, that's the point 1, 0, for example. So the cosine of 0 is 1, sine of 0 is 0. But for all the other sort of in-between angles, we're either talking about a 30, 60, 90 triangle, or we're talking about a 45, 45, 90 triangle. If it's a 45, 45, 90, then both the sides are square root of 2 over 2. If we're talking about a 30, 60, 90, then it's always 1/2 and the square root of 3. So here, all I do is, I know that 1/2 is less than the square root of 3 over 2. So wherever my triangle ends up, I always know that that's the short side and this is the long side. And I think it's pretty easy to see or imagine that when you're only 30 degrees past here, the y-coordinate is the short side and the x-coordinate is the long side. And then you just have to make sure you get your signs right, your SIGN signs right. So that's a negative and a negative. So the sine of 7 pi over 6 is negative 1/2. So what's the cosine of 2 pi over 3? 2 pi over 3, you need to know where that is. That's here. Now cosine is the x-coordinate. So in this triangle here, the x-coordinate is the shorter one. That's the 1/2. So that actually also happens to be negative 1/2. So again, I don't know that you have to have those memorized cold, but I would highly recommend that you are fluent with finding them in that way that I described in the unit circle. And if you want to talk more about that with me, let me know if you want more practice with that. And then for all of the other trig functions, they're all defined in terms of these. Tangent is sine over cosine, cotangent is that upside down, secant is 1 over cosine, and cosecant is 1 over sine. So if you know how to find these, then you can find everything else. And last, what about the trig, what about sine and cosine, tangent, etc., considered as functions? Like what if you want to make graphs of them? Like what is a graph y equals sine x? What does it look like, and why does it look the way it does? Well, it's all the same values of the unit circle. It's just that we're taking, instead of calling this theta, we're taking the x values, the x-axis, to be all the different angles measured in radians as we go around, and then the y will be whatever the value of that trig function is. So as we go around the unit circle and find all our sine values, we start with a y-coordinate of 0, and then it goes up to 1, and then it goes down to 0, and then it goes down to negative 1, and back up to 0, and so on. That would be one full lap. And then, of course, you can keep going around and around. Nothing to stop you from doing that. You can go backwards. You go negative pi over 2, that would bring you to negative 1, and so on. I'll tell you a little pet peeve of mine is graphs of trig functions that just connect these and make them look like very triangular and pointy-like. That is not what they look like. That's what it would look like if this were the some sort of strange hybrid of this thing that was a square instead of a circle. But it's not that, is it? It's a circle. So they go like this, right? Nice and curvy like. So if you have to graph a trig function, you know, make an effort to make it look proper. Let's see. I'm going to make a point here that is the angle theta equal to, let's call this theta 1, equal to, let's say, pi over 2, the same as some other angle, call it theta 2, equal to negative 3 pi over 2. Are those the same? So let's first locate where they are. So pi over 2, that's here, right? And negative 3 pi over 2, that's starting from here going backwards 3 pi over 2 to here. So they're the same location, but they're not, I mean, clearly they are not the same number, right? So the answer to this question is no. Pi over 2 and negative 3 pi over 2, I mean, type them into your calculator if you want. They're not the same number. So this angle is not the same as this angle. But the sine of pi over 2 is equal to the sine of negative 3 pi over 2. That's true. But I mean, if you look at this function, it repeats its values over and over and over again. So there are many, many different angles that have the same sine and cosine value. I'm making a point of this here because I've had many, many students in the past express some confusion about this, that in some sense they actually think that these are the same thing, and they're not the same thing. They're no more the same as if you made a graph of a parabola. This is just garbage sketching here. You certainly don't need to write this down. It would be like thinking, for example, if this is the parabola y equals x squared, this is the point 1, 1, this is the point negative 1, 1. It would be like looking at this parabola and saying, oh, well, since the function gives me the same thing, that must mean 1 and negative 1 are the same thing. Well, 1 and negative 1 aren't the same thing. They happen to give you the same function value when you put them in here, but they're not the same. 1 and negative 1 are very distinct numbers, just as pi over 2 and negative 3 pi over 2 are completely different numbers. So let's try to avoid that confusion. Other confusion comes from working with the inverse trig functions. And in general, you know what inverse functions are, I think. You've been learning about inverse functions since your very, very first days of learning mathematics. For example, not long after you learn to add, that 2 plus 3 is 5, you learn to subtract, that 5 minus 3 is 2. And all along the way, every time you learn, if you think about all the things that you learned how to do in math, every time you learn how to do something, then very shortly afterwards, you learn how to undo that thing. And I hope that I don't have to convince you that that's important, that if you're going to learn how to do something to a number, then you need to be able to undo that, that same thing. We don't want to only be able to do things to numbers and never be able to get back or undo the steps that we did. And everything you know about solving equations, variables on both sides, all these things are based on undoing things that were done to those variables. So likewise with trig, if you know how to do the sine of an angle, well, we'd also like to be able to do the inverse sine, or in other words, I think I might have done this in one of your other notes videos, but if this is the sine function, if you put a number into the sine function, an x value, the sine function says, oh, this is an angle measured in radians. Right? That's what the sine function assumes that number is. And then it pops out the other side, the y coordinate from the unit circle. Right? That's what the sine function does. So the inverse sine function, if we want to be able to undo that, we would like to be able to take one of these and get one of those. So the sine inverse function, which we write like that most of the time, sometimes it's written arc sine, would like to be able to take that y coordinate from the unit circle and give back the angle measured in radians. So if I asked you, what is the sine inverse of First of all, what kind of numbers can you take the sine inverse of? Think about that for a second. What's the sine inverse of 2? Well, that's like asking, if 2 is a y-coordinate on the unit circle, then what's the angle that goes with that? Well, that's a bogus question because there are no points on the unit circle that have a y-coordinate of 2. If you're trapped on the unit circle, you can only ever have y-coordinates and x-coordinates between -1 and 1. So this is undefined. If you type that into your calculator, try to do that. Let's see, what error message will it tell you? It'll tell you something about the domain that you've tried to put in something that's outside. It'll say domain error or something like that. I'm looking around to see if there's a calculator here. Well, you can try that and see what happens. So, can't do that. So let's try one that's a good one. So how about if I said, what's the sine inverse of -1/2? So what's your thought process here? Again, I think this is something you want to do without necessarily making a picture of a unit circle. I want to just kind of imagine here. But your imagining might go like this. So here's a unit circle, and a y-coordinate of -1/2 is here. So here's a couple angles that would satisfy that. The question is, which one is the right one? If we want this to be a function, we have to all agree, whatever you put in here, we all need to get the same angle. If we didn't, then we would have one x-coordinate, one input that goes with multiple outputs. And if you think about graphing that, that's a vertical line test fail. You would have points stacked up on top of each other in a vertical line. So that is no good. We would like this to be a function. We would like, for example, when we plug this into our calculator, to know definitively what it's going to tell us, right? We don't want multiple different answers or like randomly to pick one of these or something like that. So we all have to decide. And this is the way that we have decided. And if you want to decide differently, well, that's just too bad, because the community of people who do math in the world has already made this decision a long time ago. It's a done deal. What we have decided, I say we, I wasn't really in on the decision either, just in case you were wondering. We're going to always pick the representative angle from the right half of the unit circle, between -π/2 and π/2. So what should we say sine inverse of -1/2 is? It's this angle right here, but that's not 11π/6. That's not in between these, right? That's not in the right range here. So we're going to say that it's -π/6. And if you're thinking to yourself, well, that's the same as 11π/6, then you weren't paying attention here, right? Those are not the same thing. Those are not the same number. So there's only one sine inverse of -1/2. It's -π/6. Why did we choose this side of the unit circle? Well, the best guessing that I can do about that, I mean, we could have picked π/2 to 3π/2. We could have picked any half, any like right or left semicircle would do, right? Because that would we just need part of the circle that captures all the possible y values from -1 to 1. And the reason that we picked this one, I suppose the biggest reason is this is the interval that contains 0. So that's nice. Right? It would be kind of weird to have π/2 to 3π/2, just sort of like floating out there. It's nice to have an interval that includes 0. Right? So there you go. There's that. And I think that we're almost at half an hour, and that's enough trig. And I think that that's pretty much all of the basics that you need to know.